We've seen that we can use L'Hopital's rule to evaluate limits that produce the indeterminate form 0 over 0. So if you have a limit where the numerator goes to 0 and the denominator is also going to 0, then we can replace the numerator with its derivative and the denominator with its derivative and take the limit of that instead. And that's L'Hopital's rule. The reason that this makes sense is if both f and g, the numerator and denominator, are going towards 0, then what the ratio does depends on which of these two functions is sort of going to 0 faster, right? If f is going to 0 faster than g, then the denominator should always be much smaller than the numerator should always be much smaller than the denominator, and this ratio is going to end up 0. If the numerator f is heading towards 0 much more slowly than the denominator, then the numerator will be much larger than the denominator, and this fraction could get very large. So what this limit does depends on how quickly f and g go to 0, but how quickly they go towards 0 can be described by their derivatives as x is going towards 0. And that's sort of an intuitive reason for why it makes sense for these derivatives to show up. But it turns out that there are other scenarios where what's important in a ratio is how fast the numerator and denominator do their thing. Those other situations look like this. So if the numerator and denominator are both going to 0, not at some finite number, but as x goes to infinity, well, again, the ratio depends. The fact that we're taking a limit at infinity instead of at a real number a really doesn't change the logic of the fact that what determines the value of the ratio is how fast f goes to 0 compared to how fast g goes to 0. And so even if this limit is at infinity, the same L'Hopital's rule kind of formula applies. So if the numerator and denominator both go to 0 as x goes to infinity, then you can replace them both with their derivatives and take the limit of that instead. This is still the indeterminate form 0 over 0 because these individual limits are 0. The only thing that's different is where we are taking the limit, not what indeterminate form the limit produces. But there is another related form of L'Hopital's rule, which is what happens if you take a limit and f and g both go to infinity instead of to 0. So again, if f and g both go to infinity, what their ratio does really depends on how quickly they go towards to infinity. If f goes to infinity much more rapidly than g does, then this ratio should be big. And if f goes to infinity much more slowly than g does, then this ratio should be small. So the value of this, the limiting value of this quotient ought to depend on the rates of change of f and g. And that's reflected in the fact that we get the same L'Hopital's rule kind of formula for this indeterminate form. But this indeterminate form, since f and g are both going to infinity, this indeterminate form is infinity over infinity. So the upshot of all of this is whether you're taking a limit at a finite number or at plus or minus infinity, and whether you get the indeterminate form 0 over 0 or infinity over infinity, you can always just replace the numerator with its derivative and the denominator with its derivative and take the limit of that instead. And that's sort of the bigger picture of L'Hopital's rule. We have two indeterminate forms we can use it with, 0 over 0 and infinity over infinity. To see how this works, let's look at a couple examples. So first example, let's find the limit as x goes to infinity of e to the x over x. Now this is the infinity over infinity kind of indeterminate form because the limit as x goes to infinity of e to the x is infinity, and the limit as x goes to infinity of x, the denominator, is, well, of course, that's also infinity. So this is an infinity over infinity kind of indeterminate form. And L'Hopital's rule says that we can, instead of taking the limit of the original, we can replace the numerator with its derivative, and the derivative of e to the x is e to the x. And we can replace the denominator with its derivative, the derivative of x is 1, and evaluate this limit instead. Well, this limit, this is just the limit as x goes to infinity of e to the x, and that one's infinity, right? As you raise e to a larger and larger power, the expression gets huge very rapidly, so that limit is infinity. You can see that even though the indeterminate form we got was infinity over infinity, the actual calculation for computing this limit works much the same as in the 0 over 0 case. All right, let's look at another example. How about this one? So the limit as x goes to infinity of x plus x squared over 1 minus 2x squared. Now, this is the limit at infinity of a rational function. So for this one, we actually do have other tools we could use to calculate this limit. But let's use L'Hopital's rule anyway, just because, well, because we can, I guess. This is the indeterminate form infinity over infinity, right? The numerator as x goes to infinity, this quadratic blows up to infinity, but so does the quadratic in the denominator. Well, the denominator actually goes to minus infinity, but still, it's infinity over infinity. That's indeterminate. So we can use L'Hopital's rule. We get the limit as x goes to infinity of, taking the derivative of the numerator, we get 1 plus 2x. And then taking the derivative of the denominator, we get minus 4x. All right, now if we try to take the limit as x goes to infinity, we again get infinity over minus infinity. So this is still indeterminate, but we can use L'Hopital's rule again. Using L'Hopital's rule repeatedly doesn't always produce a result after finitely many steps, but sometimes it does. And in this case, it certainly will, because we're dealing with polynomials, so eventually we're going to run out of degrees. Okay, so taking another derivative in our numerator, we get 2. And taking a derivative in our denominator, we get minus 4. And now there's really no calculation to do for this limit. This is minus 1/2. Of course, that does correspond with what we would have gotten if we'd used our algebraic tricks to calculate this limit at infinity.